You see that?
Yes.
Let's see. We already talked about that Grignard mechanism. So is it the Grignard? Is it the coupe rate? Is it the different reactions? What area do we need to touch on?
I feel like it's the coupe rate.
Uh-oh.
And maybe like just going over the mechanism itself, kind of.
Right. The Gilman reagent.
Yes.
Yes. I think I'm confused about the specific part where you say that it only transfers one group. Because like I know
Yes.
on the quiz I got that answer wrong. The product.
Yes. So it does only Dolby makes me sick sometimes. It does only transfer one group. So once you make a group rate, right? That's you add, if you can see right here. Right. So you can see right here, like you got to start out with 2 moles of a alkyl lithium plus copper iodide. And then when you do that, I don't want to see no AI assistant. When you do that, you add 2 groups here. Right.
So
Is that part? What about that part? Is that clear?
are we always starting off with 2 moles?
If
Like,
you want to make the cuprate, yes, 2 moles of alkyl lithium or organolithium, because it doesn't have to be an alkyl lithium. So that's just a way to actually make it. So you can see right here, like there's a subscripted 2. If I can get that to highlight, and I can't. Right, that number means that there are 2 groups attached to that copper. So you can draw it and show the groups, or you can draw it and put it in parentheses with a subscript. But when that cuprate does a coupling, only one of those groups is going to transfer in coupling. The other one is going to stay on copper. So that's when you hear me say that, that's what we're talking about. So if you look right here, right, let's say for this reaction, right, here's my cuprate, or I can draw it out.
Yeah, I can see now.
Okay. So you got the copper with the subscripted 2 telling you that you got 2 groups attached to that copper. It's the same thing. And then when you react that with an arrow halide, which is what this is, right? It can be an alkyl halide, it can be a vinyl halide, it doesn't matter. Only when that copper reacts, only one of those groups is going to couple with that aromatic ring. So that's how I get the product that's shown right here. And then what's left over is this. So copper with one group attached. So when we say only one group transfers, that's what I'm talking about. It has 2, but when it does the coupling, only one of those groups couples and the other one stays back with copper. And then so you have that plus uh, lithium bromide. So anytime you have a Gilman, it has 2 groups on it, but when it engages in that coupling reaction, only one of them is going to actually get transferred in the process of coupling. Questions about that?
that makes sense to me.
Mm-hmm. So as far as the mechanism is concerned, that's really not a. I actually looked. I've been looking for years, and I probably need to go back to the old literature to find it, or old book, like some book from like the '60s or the '70s. But I have not been able to find an actual mechanism, like a catalytic cycle, to describe how this actually takes place. I'm assuming that there's probably some steps because it's not done in the presence of another catalyst like a nickel or some other transition metal where you can have that transmetallation step. That it doesn't happen like that I know of. But I have yet to find a good proposed mechanism for how this coupling takes place. I could surmise how it takes place, but I want to know for sure, like how it takes place, because I know that copper has a negative charge on it, and I also know that you can't do direct substitution on an sp2 carbon. So it's got to be some type of oxidative addition followed by reductive elimination, but I have not found a good mechanism to describe that. So that's why I never presented the mechanism for the reaction in class because I didn't want to, first of all, I didn't want to throw you off for a loop by just proposing one and then having to explain what oxidative addition is without y'all having seen that before. But now you have seen it. So, because it was in the Kumada, the Grayard video. But at any rate, I think I'm okay with you just knowing like what happens in the coupling as opposed to how it happens for this particular reaction.
So there's a the Gilman, does that start off with an organolithium?
Yes, the way you make it, yes,
Oh, so like basically an lithium is a type of organometallic,
it
but
is
we don't see it by itself, but more so with the
making the Gilman.
yes.
Mhm. It can exist by itself, but it's not very good at anything except for really just being a base. Like they're very basic, and so organolithiums are really reactive. So they react with protons, they react with the water in the air, but they're mostly used as bases
Hmm.
where they do proton transfer. So that's why we don't haven't talked about them as coupling agents because they don't do that.
Oh, okay.
Yeah, that's a good question. But they are the precursor to the Gilman reagent. So you make the organolithium first, and then you react it with copper. And then when you do that, 2 moles of that organolithium plus copper iodide, you're going to get a Gilman reagent. And this is actually, I think I talked about this one day in class. That's actually one of the drawbacks that you literally have to throw away the copper and a whole functional group. And it can't be used for anything else because once that first coupling happens, the copper is dead. It's so unreactive that you can't do anything else with it. That's why this reaction is not used for coupling as much. Is more geared towards that conjugate addition reaction that we talked about. Other questions? Did that answer your question, Yasmin?
Yes, sir.
You feel more confident now than you did 19 minutes ago?
Somewhat. I just don't think
So
I'm good at organometallics. Like it's
stop.
weird.
Don't
I
tell yourself that. You're good at whatever you put your mind to. You just gotta figure out how to attack it.
yeah.
What other questions do you have about organometallics? Because we got time.
I feel I truly, you ever not know how to do something but don't know how to ask the question either? That's what it is, because I've been watching the videos. I feel like I have to watch the videos again and like go over it again because it's for some reason it's just not clicking.
So is it the coupling? Is it the addition to carbonyls? Because we've talked about this in terms of only 2 applications, right? Coupling reactions and then carbonyl additions. So which one is the most problematic?
I'm looking at this what's it called? The sheet that we had. And the coupling is the CMRX thing, right?
Hmm.
Yeah, that's what it is. Because I'm looking at the page with the what is it says draw the product of each reaction.
Each coupling reaction.
Yeah, and that it just didn't click of how to do it.
I'm gonna paste that in.
Yeah, it's that page.
Yeah, I'm gonna paste it, and I'll paste it in whiteboard. I don't know if y'all use this whiteboard app, but I love it. So, which all you want to walk through all of them?
Yes.
All right, let's start here with the problem child. Right on the left, let me zoom in on that. On the left, we actually have organolithium. Is that right? How do I know that's an organolithium?
The carbon attached to a lithium.
Yep. So now that we know that, and then we have copper iodide, and then notice the stoichiometry. We got 2 moles of that organolithium. So we can actually, I mean, this is actually a Gilman synthesis. Is that right?
Gilman is anything with the copper.
Yes.
Okay.
But this is exactly what we were just talking about. This is how you make them. You got 2 moles of organolithium plus copper iodide. And so each one of these groups here highlighted, right, with this carbon right here being the carbon that's bonded to lithium. That same carbon is going to be attached to copper. So on the other side of the arrow, I'm going to just write that out. So I'll write my copper, and then that's the same group. And then over here, same thing. Right. Plus, and then the lithium is here with copper because that's actually positive, and that copper is actually negative. And then you have since you had 2 lithiums on the other side, right, because of the stoichiometry, it's 2 to 1. The other lithium is just going to end up with your iodide. So that's how, so it'll be that plus lithium iodide. But I don't like, that's not something I care about, but I just want to make sure I point out that it is what it is. So this is an example of a Gilman. If I took that and reacted it with, let's keep pushing this example. Why not? Since we're not in class, we can play around with this a little bit. So if I take that plus this, what should I get from that? If I bring in that arrow iodide plus this Gilman.
Oh, wait. So, okay, now I'm a little confused about this. Like the one highlighted in purple. How did that even get there? Because I see you highlighted the I see you highlighted those
Right
lines.
here. Mhm.
Okay. So,
And I had 2 of them that I'm reacting with copper iodide.
oh, that's how you okay, that's why there's two of them.
Yeah. But I just didn't write out the CH3s, right? But we can do
So,
that if that'll clarify.
see, oh, okay.
Okay, I have a question.
Go ahead.
And like the other way we could draw this is if you draw just that, like just one of them, and then do the parentheses with the carbon in between it.
Yep.
Okay.
So you
But
can do this. It means the same thing.
so
As long as you
okay.
got the subscript as a 2.
So okay. You see how you put that dot by the lithium?
Mm-hmm. Come on the other side.
Yes.
Mm-hmm.
Why are we? I thought we were coupling the carbon and the metal with the
Well, we are, but the dot is just to let you know that there's a carbon there that's connected to lithium. Because you're skipping ahead to the coupling part, but
oh
in reality,
we haven't even done that yet.
nah. But you can put I mean, the dot is just representative of that carbon, so that you'll know on the other side over here that that carbon needs to be connected to copper.
Okay,
Because
so
let me tell you why I did that. Because this is the temptation to draw it like this,
mhm.
right? But that's not right because you lost the entire carbon. So I put the dot there so that we'll understand that that's the carbon that's actually bonded to copper. Does
This
that
is
make sense? You see how you have this like it's like an isopropyl group, but really like an isobutyl group.
That's why it was never making any sense because it's like looking at it backwards. Because
Mm.
I'm thinking I'm supposed to take that lithium line, the carbon and the lithium, that line gets attached to the Cu, but you're taking everything left of that.
Yes, the whole functional group has to attach.
Oh, but not the, okay, I'm actually getting it. That makes so much more sense.
That's good.
Okay, perfect. So my question is, so you see how you drew the product? Where this is that line? You see that line? You see the copper?
Hmm.
What's the lines attached to it? Is that Li with the little dot?
Which lines though? Is it you talking about right here?
Wait, where's your mouse at? I don't see it.
You talking
Yes,
about that?
yeah, where those lines come from?
Okay,
It's
what is the definition of an organometallic?
oh, a carbon connected to
A metal.
oh, so that's why they all have that little weird gap.
Yes, because there's
Oh,
an actual covalent bond between the carbon and the metal. That's why I put the emphasis on that dot to make sure you know that it's that carbon where your carbon metal bond is forming.
perfect. That makes so much sense. So basically, the metal in that carbon, do you draw a dot and then everything behind that you attach?
You can't break any bonds, right? So that
Hmm,
whole group, that whole functional group, whatever it is, it's got to come with the carbon that's going to attach to the metal because it's if there are no bonds being broken in that on those substituents.
that makes a lot of sense. I'm trying
So
to
now what about the second part? What about bringing in an arrow iodide and react it with that Gilman? What do you think is going to happen?
with the this one right here to the with the
Hmm.
when the basically you take that oh dang you erased it. It was that, right?
No. That wasn't it.
Oh,
That
is this
was
one though, right? The C
mhm.
the okay. You would take that, but do we connect it to the copper or the lithium?
Neither. Let's
Oh,
think about it.
So the copper doesn't go to iodine, and then the other group doesn't go to lithium. I mean, yeah.
Mm-mm. Let's think about what we get ready to do. So this is CM, is that right?
yes.
And then this is
XR.
RX. Is that right?
Oh, wait. How does it go? CMXR. Is this supposed to be? Hold on. I done learned it the wrong way. I had did A.
No, you didn't. You didn't learn it the wrong way. It doesn't matter how it's arranged. The
Uh-huh.
goal is to do this, to
Oh,
take
it's
C
EX and
and
then
R.
MR. The C
No,
and the
no.
X. Oh,
Oh, on the other side, you mean?
yeah.
Yeah, sure. Yes.
So
It doesn't matter.
we put
So
that
let's
ring
do
right
that.
there. Where
So we redraw the ring. I agree with that. And let me redraw it how I have it. I don't want to confuse you. So it's this. So noisy. And this is R, yes?
Yes.
And I want C attached to it. Is that right?
Yes. So you're about to
Okay.
draw that whole thing right there.
Yes, I am,
Yep.
including the carbon that you see the dot that I just redrew.
Yes.
That's the carbon that's bound. So I have that, and I'm gonna draw it this way.
You got to draw an oh.
Is that right?
Yeah.
Isn't that the same thing?
Pretty much.
So
It is.
basically,
Oh,
so
more.
what you just drew is the coupling part.
Yes.
And then so with the coupling part, there should be no metal or no halogen.
Oh yeah, no, no, no. The metal is still there because remember there are two of those groups on copper, right?
Right.
So let's show that. So we only couple with one. So we're gonna redraw the copper like so with that one group still attached to it.
Right, but that's like the byproduct, right?
It is, it's a side product, it's
Okay.
trash. When we can't use it, but we still gotta show it. So that's the other part. And then plus lithium iodide, right? Because the iodide that's on your arrow halide right here, change the color on that. That iodine right there is going to end up with the lithium that's attached to copper. Well, it ain't really attached, but it's attracted to it.
So that's what, okay, okay. So first, I'm trying to put it into perspective of like order. So first
Mhm.
we would have to draw the product and then we would have to couple after.
Well, this is the couple product, isn't it? Isn't that CR?
Oh no, no, I meant like after we draw that thing on the left,
Mhm.
then we would couple into what we just did now.
Yeah.
Okay.
You mean after we do this right here?
Yes, yes.
Yeah. And then that's why I extended the example. So we made that from here, right?
Mm-hmm.
The 2 moles of that plus copper iodide to get to here. And
Mm-hmm.
then I extended the example by taking the cuprate that I made and just adding in an arrow iodide so I could show the coupling part.
Yes, it makes sense.
Here, you and Valentine both waking up. I can't see who else is on here though. Let me see. Okay, it's the same three people. That's
Okay,
good.
that makes
Oh,
sense.
got Kamani on here too. Okay. And how do I pronounce that? Is it Jamila or Jamilia? Help me out so I don't mess it up.
You said it right the first time, Jamila.
Jamila, I bet. I just don't want to be guilty of mispronouncing. All right.
I
Other
appreciate it.
questions? Yeah, yeah, no doubt. Other questions about that? That's the good thing about recitation. You can take some liberty with the examples and come up with new stuff, new problems to think about. All right, let's see what you got for this example. Since we're talking about coup rates, what's going to happen here?
So you're going to take, you see where that parentheses is? That's where that's
Hmm.
going.
Oh, Yasmin, wait, give us a second.
Oh, my bad. Oh, you was asleep. Let me get on this iPad. Hold on.
Right. Remember the strategy is CM plus RX. This is the goal to make CR. Now the MX part is is kind of subjective. It's really a limitation in my model, but it's okay. Because if you're using a Grignard, it's easy to see MX, but with the Gilman, it's not so straightforward because the halide, there's really no metal halogen attraction other than the lithium part. But the CR part is ubiquitous. You can use that for any coupling reaction.
Okay. Whenever everyone's ready.
Are we ready? Valentine gave us our marching orders. Whenever y'all ready. Whenever y'all ready, y'all can go now.
Ready.
All right,
Okay.
where is CM in this example?
CM is the
Remember, M is
carbon.
for my metal. So once you identify the metal, the carbon bonded to it is the C.
Mm-hmm.
Oh, the M is the copper.
Yep.
And then the C is the next carbon.
So right here, put a dot. I'm gonna put a dot right there because that helps me to track where that carbon goes in the product. Now, what about RX?
So carbon down from the iodine.
This is gonna be RX right here. Is that right?
Mhm. Yes.
So I'm gonna take that carbon and put a dot right there too, because those are the two carbons I want to put together. If that
Wait,
makes sense.
can you clarify R and X, what those are? The X.
The X is typically a halogen, but it's whatever the leaving group is.
Okay.
So in this case, once I identify that halogen in my aryl, alkyl, or vinyl halide, then I know if I know what that is, I know the carbon connected to it is the carbon that's going to participate in coupling.
Okay. That makes sense.
Because it's
Okay.
only that halogen is necessary because you have to insert into that carbon halogen bond in order for coupling to happen. Where there's like a dot, like in this case, this probably happens kind of similar in a similar fashion to the conjugate addition. You know how we did like the copper attack, that soft carbon, and then you did reductive elimination, and then all the rest of the steps that ensued after that. So this, because it's a sp3 carbon, is probably the mechanism is probably similar to like just a substitution. Similar, but not the same.
Conjugate addition is in this packet, right?
It is. It's the last example on here too. We can talk about it.
Okay.
So let's go to here. Now we're gonna take these two and put them together. So we got a 3-carbon chain. 2, 3. I'll put a dot right there. And then that is going to be connected to the carbon where iodine was on that aromatic system. So you'll have this chain right here.
I drew it a little weird.
That's okay. And this group right here, the whole thing.
Mm-hmm.
Then I have that. And then I'm going to do this. I'm just going to write the aromatic ring in right here. That's it. Right. And this, I think the key is to understand why why we even want to do it. Because this is a very efficient way to make carbon-carbon bonds. And that's important because all your natural products, all the natural products that I've shown y'all in class that have all this biological activity, you can find it in nature in abundance, you got to be able to make it. Because some products like, I'm going to show you one right quick. And I'll make the point about why it's important to be able to make this stuff. It's like this right here. Y'all ever heard of Taxol? Can y'all see my screen still?
Yes.
See how complicated this molecule is? So this is Taxol. It's a anti-cancer drug. It is my first wife who passed away from breast cancer. They gave her this drug at one point during her treatment. Uh, it's a very powerful chemotherapeutic. And but the fact that it takes 100 years for the tree that this comes from, because it comes from the bark of a tree called a Pacific yew tree. It takes 100 years to grow one of those trees. And even if you harvested all the bark from the tree, you're only going to get a few milligrams of this. Now you think about you got a milligram of Taxol and you got 1 million cancer patients. That's not even enough to treat one patient. So you got to be able to make it. And the best way to make carbon-carbon bonds is one of the most efficient ways and one of the cleanest ways is to do coupling reaction. There are a lot of other ways, but the coupling reactions, you can build up all this type of scaffolding like really quickly. So that's why we're learning about this because it's a very important method for carbon-carbon bond formation, if that makes sense. Yeah, her oncologist used to be like just tripping out because every time they try something new, I have my laptop like pulling up the structure and looking at like thinking about how it was going to interact with the cells and all that stuff. And they just got a kick out of that.
As you should. Sorry for your loss.
I appreciate that. I
Sorry.
appreciate that.
Yes.
All right. Any other questions about that part?
I'm
I think
trying.
it's
Hey,
clicking. I
I
think
got
it's
a
clicking.
question. I'm not gonna lie.
Go ahead.
When it comes to that MCRX or CMRX thing,
Mhm.
when you talk about the leaving group, when you find out what the RX is and what the MC is,
Mhm.
I seen that methyl group that CH3 in the parentheses two. Why isn't it two of them on the product?
Good question. So again, if you're using a Gilman reagent,
Uh-huh.
it can only transfer one group.
Okay.
So this is one of those groups right here. Let me put that methyl group back in too, so you don't get there's no confusion about that. So
Mhm.
that CH3 is right here. Come on, pen, stupid. Sorry.
Okay.
That CH3 is right there. The same one that's right here, right? But
Right.
then the side product is this. So you got a copper with one of those 3 member chains still attached to it. It's the only thing I hate
Mhm.
about this whiteboard. So you still got that, right?
Mhm.
Left over
So what happens to the lithium?
is right here. So you got that, and then plus
Okay.
lithium, and then whatever that X is. In this case, it's iodide.
Okay.
Yeah, but you can think about that as LIX, right? So whatever the X group is, it can be iodine, bromine, chlorine, it doesn't matter. When you do the coupling with a Gilman, that halogen is always going to end up with lithium.
Okay. Okay. Okay.
Mhm.
That makes sense.
Yeah, good question. All right.
Okay.
Go ahead.
I have a question. So, can you like make or tell us a list of things to learn with organometallics? Because allylic bromination is just that. The retrosynthesis is just that. So with organometallics, is it coupling, conjugate addition? Like
Yep.
what's everything?
Retrosynthesis, because that's the retrosynthesis product
Mhm.
is hold up, I think I gave y'all that already. Let me see something. I'm gonna go to Canvas
Mhm.
because I think I in the last set of notes I actually went through and did a overview. I just want to see because I actually in that last set of announcements I think I put a kind of like a little guide in there somewhere. Let me look. It's my bootleg AT&T Wi-Fi. That's why it's taking so long to download. So there's an overview. Like, yeah, I did. It's this set of notes right here. So with the organometallics, you got really 3 things to think about. And each one of those concepts has, of course, other information. But the concept map right here is that you can do coupling, which I have shown on the right side. And then on the left, the organometallic is in the middle. On the left is carbonyl addition. And then below it is the conjugate addition part, depending on what type of. So conjugate addition is specific to Gilman reagents. Coupling can be Gilman or Grignard. And then carbonyl addition is specific to Grignards. So with that carbonyl addition, you know that you can get that other information is what type of alcohol am I getting? Secondary, tertiary, and how do I know? Well, if I start with an aldehyde, I get a secondary. If I start with a ketone, I get a tertiary. If I start with an ester, I'm going to need multiple equivalents of the Grignard to take that ester to an alcohol. Right, so I think I have that down somewhere down in here too. So this page has the conjugate addition with the mechanism, and I had another page that's the Gilman section. Then here's another overview of the different types of organometallics and how to make them. Right, so the Grignard, the organolithium, and the Gilman, and then there's a short section, a generic section on coupling in here too. But let me, yeah, we don't need to talk about that. Well, unless y'all have questions about it. Let's see.
I was gonna ask you, so you said that, so are those the mechanisms we're gonna have to know for the test, like the conjugate addition and the carbon
Mm-hmm.
addition?
Yeah, and it may just be like, instead of having you draw out all the steps, it may be like a supply the arrows where you get the intermediates and the products, but you have to put the arrows in to show like how you got from point A to point B to point, from point B to point C, like that. And then with that Kumada coupling, that catalytic cycle. I understand that can look daunting. So that question will probably be like something like a matching question where you have to identify the steps. Which step is oxidative addition? Which step is transmetallation? Which step is isomerization? Which step is reductive elimination? Right, let me scroll back up to that. I need to be able to rotate that. Let me download this so I can rotate it. That page so it won't be so hard to read. Wouldn't trade it for the world. It's like right here. This is like that Grignard coupling mechanism. I don't need to read the page. I already read it. So of course you have these different steps in this mechanism, and they were also in that the video going over the catalytic cycle too, and what happens in each step. But this would probably be more like a matching problem as opposed to me asking you to write out the mechanism for this. But the mechanism for carbonyl addition, that's pretty straightforward. So that may be a proposed a mechanism type question. And
Okay.
then if it's something more robust that I feel like it could take you a long time on an exam, then I may just make it like a supply the arrow type question too, where you put the arrows in.
Okay. And so you know how when we was just going over the Gilman uh stuff, and you said that
Mhm.
there's no real like you haven't been able to find like a mechanism for the couple,
No, I wouldn't ask you for that.
right? So, but this is the mechanism for coupling for the Grignard, right?
Yes.
This is okay, and then
So so this will probably be like I said. I'll probably make this like a matching question where you
okay,
have to match up the steps or you have to match up the intermediates.
What's the mechanism for you said carbonyl addition?
oh yeah, that's
Hmm.
what I was trying to ask. Is there a point? Is there a paper or like in the handout? Do you go
Yeah.
over that, or was that just something that y'all went over in class?
Mm-mm. No, it's right here. But there's a whole section on carbonyl addition.
Is there a video?
Yeah.
Lovely.
If I'm not mistaken, I think didn't I send y'all a video dealing with carbonyl addition, alcohol from Greeners? I think I did. I know I sent one out. I made one for that Kumada reaction because I didn't have that in my arsenal. But the carbonyl addition, I think I sent that out. I know that I have a video for retrosynthesis. So let me see. I can pull it up and prove it. I may be just tripping. I gotta take some time and update some of these videos. That kind of when I first started doing this flipped classroom thing, that was like you can see 11 years ago. So about 2014. I remember making like over the summer, I probably made like half of this list in like 2 months. And then other videos I just made as I saw that I needed them. Let's see, outcomes. That's part one. Stereochemistry. Yep. Oh, here's the video right here. Gradient addition to aldehydes, ketones, and esters. I sent it out though. It's in one of the announcements. I'm not sure which one, but it had to be at least some either last week or the week before. Might have been last week.
Okay.
Actually, since we're already here, let me find it. Go back to Chrome. So I can just look through the announcements and see which. Why is Chrome not coming back up? Yes, I think it's in this video, in this announcement from the 17th. Wait a minute.
Okay. Thank you.
Couple of
The
reactions.
the part one video, I believe I just had it on there. The part one video, you did say you wanted us to know those coupling techniques, right?
You're talking about for the grain,
Yeah, I
because
believe.
that's what this is. These are I had to break that video up into two pieces because it was too long. But this is the same. This is this video right here. Where is it? It's probably at the bottom because I didn't move it.
Because it was the what's it called?
The model reaction.
There was a still one, still, and then
Oh,
some,
Stille coupling.
and then there was another one. I don't know how to
Yeah,
pronounce it.
that'll probably be it was Stille coupling, Heck coupling, Sonneger coupling, Nagishi coupling. Yeah, I gotta reorder these. I'll put them up where they belong. But yeah, I no those reactions. I'm not expecting you to know how they work or anything like that, but it may be a bonus question or something about it.
Oh, I thought you wanted us to know how to do that.
No, because I didn't. I my point of doing that was to show you that this stuff is like this is real chemistry. So all these coupling reactions that we've been talking about, there are a lot of ways to do coupling.
Mhm.
Um, but this is the like bare minimum, the bare bones basic coupling. But on a more advanced level, you can do. I mean, there's some really sophisticated methods out there to do coupling.
So as long as we know, if we sit and know how to do these worksheets that we're doing in class and listen to the video, we should be fine, right?
Yeah, but you should have already been listening to the videos at least.
Oh no, no, I bet now you know I already
I
know.
know, I know. I'm just saying I can't speak for you, but I know like
Yeah, I get
I
what
know
you.
how it is. I've been teaching this class for a long time. There are people who are gonna be watching, trying to watch all the videos Tuesday night before the exam. And it's not gonna work. But yeah, so topic wise, we did a little bromination. So you know you need to know that mechanism, which
Mhm.
is the initiation, propagation, termination steps for that. And you need to be able to do resonance because that was part of that topic. Um, then when we got to organometallics, we talked about the different types, the granular, you need to know how to make that, even though you don't need to know the mechanism, but you need to know what's necessary to synthesize it. So magnesium, alkyl halide or aryl or vinyl halide, low temperature. Uh, if you look through that last set of notes I posted, all the information is right there. It's all summarized
Oh,
from every section.
and then resonance was the radical thing, right? Or what was resonance?
Hmm
Okay, yeah. And then, okay, the last thing, I just wanted to ask if you could do like one problem from like that sheet with that we were just on, not that same sheet, but the one after it.
The one we did yesterday in class.
Mm-mm. No, we
Uh,
did synthesis. Oh wait, did we?
We did a
If
bunch of stuff yesterday. Not well, yeah. Yesterday was Wednesday. Yeah. It wasn't this, it was like a practice sheet that I had. I used it in a previous class.
what was this? Oh yeah, that is the practice sheet that we did yesterday.
I
Okay.
didn't, I didn't, I uploaded it to Canvas yesterday. Let me see. Uh Canvas I had open in Chrome. Let's see. I'll find it. Because I think I uploaded the whole thing. Yeah, it was this sheet right here that we were working on. Is that the one you're talking about from the other day?
Mhm. Okay, yeah, that is the same thing. I
Mm.
well, the question is, how do we know what to take out of it? Like, not that sheet, but the one that you was just on. It's the long list of CH3, CH2, Mg. How do we know which one we're replicating in the product?
So you're talking about this handout right here?
Yes. And you see the one on where it says number one and then it's all that chunk. How do we know what we're putting on the product? That was what was
This one,
You were just on it, the one below it.
or the back page.
Yeah. How do you
Right
know which,
here?
yeah, how do you know which one to put on the product? Because I know that that's going to be a OH. You keep the CH3, but
Mm,
how do I
but
know if I'm putting, which one do I
hold
pick
up.
on the top line?
All right, hold up. Let me come on, Adobe. I don't know what's going on with Adobe. It's just like this program has a bug in it because it just won't act right. And I'm kind of PO'd about that. Spent a lot of money on this subscription.
But other than that question, I think I'm straight now.
So asking about like this example, right? So think about it.
Yes.
When I do Grignard addition to a carbonyl, right? The Grignard, if I were to write that out in Lewis form, wouldn't it look like this? Well, let me write it all the way out in Lewis form. Wouldn't it look like that?
Mm-hmm.
So wouldn't it be this carbon that's going to attack my carbonyl?
Mm-hmm.
So that's how I know what to add. Whatever the carbon is that's
Oh.
connected to the metal, that's the carbon that I'm attaching to my carbonyl. So remember when I gave y'all this little shortcut for the alcohol synthesis, like if I were to just draw this out as an alcohol first in the product,
So
right?
everything behind it.
Everything
Say
right there.
again.
So
Oh yeah.
if I just replace that magnesium, I'll take that bond that's drawn to magnesium and I'll just redraw it right here. So it's this, and it's just to predict the products. This is not showing the mechanism. Or I can draw it in skeletal form like this, because it's just a two carbon chain, right? Both of those are correct, but it's the entire fragment that's bonded to magnesium. That's what I'm drawing as, or that's what I'm attaching to that carbonyl carbon.
That makes a lot of sense now. I understand it.
It'll be the same thing down here. If this is my Grignard, this is the carbon that's attached to the metal. So that carbon and everything that is attached to it, that's what I'm going to add to the
Okay.
carbonyl. So for that one, even if I were to draw that one out, the strategy is to predict the product of a carbonyl addition, a Grignard addition to a carbonyl. You just redraw the carbonyl as an alcohol,
And it
and then
just
the group that's attached to magnesium, I'm going to attach a 4 carbon chain. So I'm just going to attach a 4 carbon chain, and that's the answer.
for number 3, will we do it twice because it's 2 moles or just
Yep.
one?
So the first, since that's an ester that you're starting with, that's why I keep reinforcing about learning your functional groups.
Mhm.
So if it's an ester, we know that an ester plus a granular, if you do 1 mole, it's going to give you a ketone. So what's going to happen in this case is since I'm not making an alcohol from the first mole, I'm just going to replace that with this. That's the ketone. So I'm gonna end up with this first because you got to get the ketone before you can get to the alcohol. But you're right. If I have 2 moles, that means that ester is eventually going to become an alcohol. But initially, it's going to be a ketone. Then if I take that and react the second mole of granular with it, that's when I get the alcohol.
Oh, that makes sense.
That's when I can take the ketone and redraw it as an alcohol. And then I'm gonna change the color on the second mole just to make it make sense. And I'm gonna bring this in.
So we're always gonna break that bond and make it an alcohol.
Yeah. If it's a ketone or aldehyde and you add an ingredient to it, yes.
Okay.
I didn't mean to make that line bold. I don't want you to think I'm trying to make that chiral because it's not, because you got 2 of the same groups attached.
And then like the the aldehyde is the O and the H. The ester is the double bond O, and then the ketone. Isn't that a carbon carbon?
Yeah, carbon on each side. Yep.
Okay. I feel way better.
Good. That's good. Any other questions about anything? I love whiteboard. I ain't gonna lie. All right. Fire drill. All right.
Other than that, I think everything else is good.
You heard about another session on Monday. I don't know where you heard that from. Maybe Monday is my workout day. Monday, Wednesday, Friday, and Saturday. So depends. It won't be at 7, but we could do something while I'm on campus though. Yeah, we can do something while I'm on campus. If that's something y'all want to do, I'll be happy to do something before I left. All right, no problem. Any other questions? Anything else?
Just to clarify, because I'm taking like little notes on here. The aldehyde was carbon and hydrogen on the side.
Let's just draw it out. How about that?
Yeah, that's
You
perfect.
need a flashcard out because
I
I've been telling y'all about since January the 9th.
wait, it's actually on here. I wonder.
You need a functional group flashcard. That's an aldehyde. If it's 2 R groups, that's a ketone. And then for ester, it is OR. But R doesn't, it can't be hydrogen. It's got to be a carbon.
It has to be a double bond too, right? For one of the oxygens.
Oh yeah, that's all of these are different carbonyl groups. So this is what makes it a carbonyl right here. All of them are carbonyls, but what's
Oh,
attached to the carbonyl carbon is what differentiates uh, them. So aldehydes have a hydrogen right here. Ketones have carbons on either side. Esters have what's called an alkoxy group.
Hmm.
So OCH3, O ethyl, O methyl, like that. And this is a aldehyde
Oh,
ketone. Right. This is one section in part one that is, if you don't learn nothing else, you got to learn them functional groups. I have
yeah.
some functional group videos, but I never share them. Well, I share them with if I'm teaching part one, but that was in my early days, so they're kind of boring, and the graphics are not that great. I need to redo them.
I'm gonna go. I'm gonna go back and look at them because I found some other videos about the organometallics that helped a little bit. I also had a question for the quiz. So I turned in every single thing except for my retrosynthesis quiz because I seen it was the little drawing thing.
Mhm.
Am I able to, because I already have the drawing, like I feel like I got it right, but before I submit it, am I able to show you like in
You
class?
mean to tell you if it's right or wrong?
Not
Yeah,
necessarily. Maybe
necessarily,
tell me.
necessarily. But yeah, I'll look at it. Just bring it with you tomorrow.
Yes, sir. Perfect.
Yep, not necessarily. Y'all think I just jumped off the cabbage truck? I really did not.
Yes, necessarily.
Yeah, exactly. Just tell the truth and shame the devil.
But other than that, I feel 10 times smarter.
That's good. That's good. All right. Well, I gotta go make me a omelet and a shake. So I'll see y'all in the AM at whenever you get there. You always early. Kamani,
On time.
I'll see you. Yeah, he's on time. I ain't gonna mess with him. All right, y'all
Well,
take care.
you too. Be safe.
Thanks. Have a good night.
You too.
All right.